In previous generations of teaching this subject, one of the things that often happens with me is I get so excited that I kind of lose track of what's most important to you guys. So this is one of those subjects that I've decided to kind of just start everything off with what you should get out of this topic. And then what I'll do is, after I've kind of shown you the most important things, we'll go into some of the theory. And I've actually found a couple of videos for you guys that do a lot better job than I was able to do with just the use of animation and things like that to make this subject a little bit more understandable. So the last time we talked a whole bunch about Lewis structures and covalent bond theory in terms of like a single line, meaning that you're sharing 2 electrons, and a double bond sharing 4, and a triple bond, et cetera, et cetera. But what we're going to do today is we're going to start to, well, first of all, do what this is saying, assign hybridization to certain atoms. Well, if you can notice, I already made a mistake when I was writing this on the board. We're assigning hybridization to atoms, and the things that they hybridize into are these things called hybrid orbitals. So what we're going to do is I'm going to give you an example structure, and I'm going to show how your knowledge of electron domain geometries, which we talked about last week, make this very, very easy. And I'll show you a little bit of how to handle resonance, and then those other videos are going to talk about all the theory that you need, and then I'll probably put another video kind of on the end of the molecular orbital video, just as kind of my like 2 cents about why we're even talking about such a complex theory that usually you only have to worry about in either physical chemistry or like say organometallic chemistry or something like that. So bear with me here. Okay, so this is going to be a great example for assigning all the different types of hybridizations that we're going to have to assign. And one of the things, like I said previously, is that you'll pick up on the fact that if you're really good at electron domain geometries, then this side of things is pretty easy. So what you'll notice here is an organic structure. It's got a nitrile and also an alcohol group in there, just to kind of get you used to naming functional groups. Also, this is an alkene, right? Or otherwise known as an olefin. And anytime you have any kind of chlorine in there, it's some sort of haloalkene, or in this case would be a haloalkene. So let's go through and first of all just assign electron domain geometries, and then we'll assign molecular geometries. And I'll show you the really, really simple way of assigning hybridizations of things. And then the next video will show you kind of the theory behind all that and what it actually means to use these crazy letters and numbers that I'm about to use. So first of all, let's just go through and assign some electron domain geometries. And if you have questions about any of the ones that I assign, please ask me, because that's really the key to figuring out this whole hybridization assignment thing. Okay, so that's probably a horrible mess as I look at it, but hopefully the video quality is such that you can actually pause the video and zoom in on a couple of these things. So obviously when I say EDG, that's electron domain geometry, right? Those are the way that the electron clouds are situated around an atom. MG is molecular geometry. In other words, what would you see if you could zoom in really close and see all those bond angles, etc. One of the things you'll pick up on right away is that you can have an EDG and have no MG, right? So anytime you're kind of at a terminal end of a chain or something, like for instance that nitrogen, it certainly has to make 2 spaces for electron domains, right? This triple bond and that lone pair are electron domains. But because there's only kind of one atom bonded there really is no molecular geometry. But when you start to get into like a carbon chain or into a molecule, you'll notice that you start to pick up molecular geometries, like right there. That carbon right there is both linear in electron domain geometry and in molecular geometry. Here's a tetrahedral electron domain geometry for a chlorine, right? No molecular geometry because it's the end of a chain. And then sometimes, if you don't have lone pairs of electrons, you'll notice that your electron domain geometry and molecular geometry match, right? So these two carbons have trigonal planar electron domain geometries and molecular geometries. That oxygen as a tetrahedral electron domain geometry because of those 4 electron clouds around it, and then you would say the molecular geometry is bent. And then of course these both are tetrahedral carbons right here. So hopefully that's not something that confuses you, and certainly if you're confused by that, that's something we have to address right away because everything else is going to be based on that. So now I'm going to go through with this red marker and I'm going to assign some hybrid orbitals. And you'll pick up on probably a pattern right away, and then I'll show you a summary slide that really is going to help you a ton, certainly more than I ever figured out when I was in your shoes. So pause just a second. First thing we're going to focus on, because this is an organic class, are the carbons. So I'm just going to pick on these 2 alkene carbons right here. All right? We know that they're trigonal planar. Well, what that means is that if this thing is trigonal planar, I got to make space for 3 different electron domains. That's why it's based on a trigonal planar geometry. Anytime you have an electron domain geometry, what you're going to be using for a trigonal plane is 1 s orbital and 2 p orbitals. Those are all going to mix together according to some of the rules that you're going to see in a couple of the theory videos. But the important thing to recognize is that if you have a trigonal planar geometry, automatically that thing is an sp2 hybrid, right? And so, as again you'll see in the theory video, if I hybridize an s and 2 p's, that leaves 1 p orbital over. So what that means is that I've got this kind of sharing of electron density between 2 sp2 hybrid orbitals. But then in the plane of this, as you'll see, like I said in the video that I posted for you, is there is a p orbital that does a side-on overlap, right? And so what you would say in terms of molecular orbital theory, what you would say is that this bond right here is made up of the head-on overlap of 2 sp2 orbitals and what's called a sigma bond, right? And so anytime you've got head-on overlap of orbitals, that's called a sigma bond. And then the sideways overlap that's happening right here, which is really tough to draw, that's called a pi bond. And so what you would say is that this double bond right here is made up of the overlap of 2 sp2 hybrid orbitals and then 1 pi bond, specifically a pp pi bond. And I'm not sure how much you went into this in general chemistry, but you can have pi bonds from the overlap of p and d orbitals. Again, that's something that we're not going to talk about very often, if at all, in this class. So, most important thing, without a doubt, like just tell me what I need to know, Sean, and stop blabbering. Well, what you need to know is to assign these 2 carbons sp2 hybrid orbitals, right? That comes from you knowing your electron domain geometry. Anytime you see an electron domain geometry that is trigonal planar, it means that that has to be made up of what's called an sp2 hybrid orbital. If we go out to these carbons over here, you'll notice it's all just single bonds. Anytime you see an electron domain geometry of tetrahedral, that means that is made up of 4 sp3 hybrid orbitals, which hopefully you can see on that screen. So that carbon is sp3 hybridized, that carbon is sp3 hybridized, and what you could say is each individual bond is the result of the overlap of 2 sp3 orbitals. This one over here, of course, like if we assign an sp3 there and assign that thing the sp2 we just did, this bond is said to result from the overlap of 1 sp3 orbital from this carbon and 1 sp2 hybridal from that carbon. That is, of course, a sigma bond, right? And so in molecular orbital theory, sigma kind of roughly corresponds to a single bond. And then anytime you see any kind of double bond or triple bond, that's going to be called a pi bond. So we could say also that oxygen, right, since that has a tetrahedral geometry, it also is an sp3. It's made up of 4 sp3 hybrid orbitals. That guy right there is the result of the overlap of an sp3 and an sp3. You wonder, well, what the heck's going on with hydrogen? Why haven't I talked about hydrogen? Well, it turns out hydrogen only has an s available, right? And so this is an example. That bond right there between oxygen and hydrogen is the result of an sp3 hybrid orbital overlapping with what's called the 1s atomic orbital of hydrogen, right? Because hydrogen can't actually undergo any kind of significant hybridization. The only other option that we haven't talked about, right, we talked about sp2s, we've talked about sp3s. Well, it turns out anything that is linear, those things are sp hybrid orbitals, right? And so this is the overlap of, this bond is a sigma bond between an sp orbital and an sp2 orbital. This triple bond is the result of one overlap of an sp-sp, right, sp-sp, and then those two other bonds are what's called two orthogonal pi bonds, right? It's overlapping like this, and it's also, let's see, so it's overlapping like that, and it's also overlapping like this, right? And so for pictures of that, it's probably best to either ask me about it in office hours, and I'll show you a really awesome site where you can kind of see all the pictures and rotate them around and stuff like that. But when it comes right down to it, the most important thing is just do your electron domain geometry, give the hybridization of that particular atom, and then you might have to dig a little deeper and talk a little bit about, you know, the head-on overlap and sigma bonds, or the sideways overlap and pi bonds, but that's much less, I guess, common, or it's a little bit too much of a complex question typically in organic class. The only other thing we have to talk about in terms of getting quick points on the board here in terms of what you need to know is how to handle things like this instant classic here that we talked about back in the resonance series of lecture slides, or video lecture, I guess I should say, is how to handle resonance, right? And so the important thing is to recognize when I write these resonance forms up here, just to show you what we talked about previously, is that when I show these resonance forms, it doesn't mean that the atom is switching between hybridization states. Oh yeah. So see how that that kind of resonance idea is something that complicates our assignment of hybridization of atoms just a little bit. Okay, so hopefully I've written up all the resonance forms that we talked about previously. And so what are we going to do in terms of assigning hybridization, and, well, I should say, what are we going to do in terms of assigning electron domain geometries? Well, there's one atom in here that's pretty straightforward, and it's not going to be something that we have to work really hard to understand. And then the other two atoms on the sides here, we're going to have to talk a little bit about how we're going to assign hybridization. So first thing we're going to do is we're going to assign just electron domain geometries to these things. Well, this center carbon and every single one of those resonance forms we would expect that thing to be linear. And we would be right? The molecular geometry would be linear. The electron domain geometry would be linear. And then, of course, if we understand our hybridization theory well enough, anything that's linear is automatically an sp hybrid, right? And so that's not hard to think about, right? So that's what my carbon looks like there. sp hybrid, sp hybrid, sp hybrid, pretty straightforward. But imagine how you would assign this thing without these resonance forms right here, and watch how you could end up with the incorrect answer in terms of your hybridization. So we look at this nitrogen and just pretend that we don't know that these exist. You might imagine that that thing is some sort of trigonal planar electron domain geometry, right? And, absent these resonance forms, you'd be 100% right. But the problem lies in the fact that this covalent bond theory that we've learned to love is just really a little bit clunky, right? It doesn't explain every situation. So it turns out that nitrogen right here is weirdly an sp hybrid, right? And so let's write that down first of all. That thing is sp hybridized. And so really, I struggle to even put electron domain geometry of linear on there, even though it has to be if it's sp hybridized. And It's because that this bonding theory that we're talking about here, it's kind of starting to break down, right? We're kind of trying to fit a square peg in a round hole. And it's like, why? Well, why is he not just calling that linear and SP hybrid? It's a little more complex than that, right? And so the real thing that we should do is we should switch to molecular orbital theory, which, by the way, the end of one of those videos does a good job discussing molecular orbital theory. And then by the time you get to my video about like things having to do with molecular orbital theory, you'll understand why it's a scary thing to jump into that theory when you have a perfectly good theory that you could kind of just, beat with a hammer into that, square hole and just say like, okay, as long as I've got predictive capacity, I don't care, right? As long as I can answer questions on the back of an envelope, I don't need a supercomputer to figure it out, right? And so that's kind of where we are right here. So it turns out in terms of hybridization now, that nitrogen is actually sp hybridized, and you'd say, well, where the hell does that come from? Well, it comes from recognizing that in this resonance form, it has to be sp hybridized to keep those two p orbitals alone, that it can actually do that sideways overlap that it needs to do in this kind of resonance hybrid, right? That's a lot of hybrid. So really, the rule that I use in terms of when there is resonance around and you have to assign hybridization, I kind of go to the least sp count, if that makes any sense, right? Like in that form, we'd expect it to be, sp2, but we're like, oh wait, there's an sp there, so that's what I'm going to go with, right? And that has to do with making sure that you don't use up p orbitals to hybridize when in fact you have to maintain some sort of additional pi bond, right? And so I know it's getting a little funky here. So it turns out that that's actually sp hybridized, and let's just call it linear to kind of keep with the way that we're learning this here. This guy down here, that sulfur, you'll notice, well, once again, we have kind of a similar situation, right, where we'd say that it was, if without these resonance forms, you'd say, well, that must be sp2 hybridized, right? And then you look down here and you say, well, that's sp3 hybridized, right, based on an electron domain geometry that is tetrahedral. Well, it turns out that between these two, we'd say, well, that must be that the sp2 wins, right? And so we'd say, well, that sulfur must be sp2 hybridized. But then you go down here and you're like, oh no, it's sp hybridized there too, right? And so what I mean by it is, like, once we're good at resonance forms, we're going to learn a little bit about, we're going to learn a lot more about this. But it turns out that S is, we're actually going to call it sp hybridized because of the existence of this resonance form. Just because I can't shut up, hopefully you understand something of what I just said. But like what we'll kind of discover, right, is like something like this we already talked about is not a really likely resonance form. So really, we could almost even leave that off the list, right, completely, which would really change our answer here. But just to stay like kind of consistent with this already kind of bizarro theory that we're kind of like, it's almost like you're to ask about the hybridization of that sulfur is to kind of to be answering a very esoteric and just kind of unrealistic question. So just to kind of like not confuse the hell out of you, I say, once you've gotten good at resonance, you see something that's got a bunch of different resonance forms, just go with the least amount of p's to allow yourself the existence of different multiple bonds. The thing that would be really incorrect is for us to look at these resonance forms, right, and to assign the hybridizations of, let's say, that S is an sp3, and then we say, oh, and then it changes to an sp2, oh, and then here it's actually an sp. That's not, it can't be that, right? In terms of resonance, remember, like the overall picture, this is trying to tell us about what the overall picture of that sulfur looks like. And the closest we can come to properly describing this thing using resonance arrows are a picture of these three, kind of a weighted average, where that thing is essentially an sp. Okay, so I probably shared too much and confused the hell out of you. Please talk to me in office hours. The good news is that usually, in terms of questions that you'll have to answer for me, the resonance doesn't really play a huge role, right? I recognize that this gets super complicated super fast, so I'm going to try my best to kind of only choose things that have like maybe 2 resonance forms if you have to assign any kind of hybridization, or better yet, no resonance forms, and then it's just that straightforward. Tetrahedral is sp3, trigonal planar is sp2, and linear is sp. Whoop, whoop, whoop.